Welcome to class meeting 23 of the Introduction to Optimization. We have two announcements related to the homework 5. It is due on next Monday. You have plenty of time tomorrow. And there are 3 additional homework problems, mainly proving some main results. First one is related to the unbounded constraint set. I have given you my own proof. But the textbook has its own proof, so please take a look at that. Second one is this one. Given a basic feasible solution, if you want to move to adjacent basic feasible solution, the objective function value can be written as the objective function value of the previous basic feasible solution plus a correction term. What you are going to prove is the formula. Okay, that is the second one. Third one is I'm not sure this is in the textbook or not, but we need to show that the simplex algorithm really generates the optimal X star when the problem is not unbounded, when the problem is bounded. So try to prove this and add it to homework 5. Okay, then let's have some quick review and move to today's topic. Last time, at the end of the last class meeting, we've seen so-called Canonical Tableau. What was Tableau? Tableau is a small table. In our case, it is an augmented matrix obtained from this one. So we start from this augmented matrix. Here, our linear programming problem has equality constraint AX equals B that appears here. A and B, and our cost function, our objective function is C transpose X, where the first M entries of the C vector is now written here as in a row vector, and the last N minus M costs are written here, and you put 0. This is your starting point. This is an augmented matrix. And our canonical tableau is obtained by performing elementary row operation to find our first initial point. Without loss of generality, let's assume that we use first M columns of A matrix to obtain a starting point of basic feasible solution. Then this becomes identity B inverse D, B inverse B, and here if you continue performing elementary row operation, then since this I sub M, precisely speaking, is an identity matrix, you can make this entries 0. In that case, you automatically have some row vector here, and surprisingly here what you obtain is minus, let me see, C sub, is it D? C sub, let me see. This is real confusing. C sub B transpose, yeah. C sub B transpose B inverse B. Okay, so what is this, by the way? This is negative of f of x0. By the way, here your x0 is nothing but B inverse V0. And sometimes we call this B inverse D as capital Y. So this is our starting point. I emphasize that the simplex algorithm is a two-phase algorithm. First, you solve an artificial problem by introducing artificial variables to find the basic feasible solution of our original problem. Suppose that basic feasible solution is this one. Then corresponding augmented matrix after elementary row operation is this tableau called Canonical Tableau. And here, this Canonical Tableau contains a lot of information. What is this R transpose? We call this as relative cost coefficients. So this is called RCC. What does this mean? Why this is called relative cost coefficients? Because as we've seen already, any feasible solution f of x, any feasible solution x evaluated for the objective function can be written in this way. Now, as you see, the x0 has this part all 0. Now, if you set xd that corresponds to here equals 0, what do you have? You have x equals x0, and the objective function is definitely f of x0 equals f of x0. Now, other feasible solutions, not necessarily basic feasible, other feasible solutions will have what? Will have this xd components, some 0 entries and some positive entries. Why we don't have negative entries? Because we assume what? We start with a standard form LP problem that constrains x vector or greater than or equal to 0, right? So this part becomes some 0 and some positive value. So entry by entry multiplication assures you that what will happen? If this R vector is all positive, what happens? If this R vector consists of all positive, definitely x0 is optimal. What if this R relative cost coefficient vector consists of some 0 and some positive value? Still, this is optimal. Because we want to find in our linear programming problem, we want to find an optimal solution. Not every optimal solution. So, as far as this relative cost coefficient vector is less than or equal to 0 vector, you have your stopping criterion satisfied. That's great, right? And what else can we say? We want to go back to this first additional homework problem related to unbounded constraint set. Probably you remember or you need to check my derivation. What happens? In that case, what I did was that our new basic feasible solution have what? Have here the Q's entry equals some positive beta. So all 0, beta 0 appears here. And what happened if corresponding y sub q vector has all non-positive, less than or equal to 0 entries? We had unboundedness because that beta could be any positive real number, right? So the norm square of that feasible x has what? Is infinity. So you remember that here if yj is less than or equal to 0 for some j between n plus 1 and n, then omega is unbounded. That's related to this one. Okay. Now, what about that relative cost coefficient corresponding to such vector yj is negative? What will happen? As you see here, if you multiply beta some positive number with some rj negative number, what will happen if beta tends to infinity? It becomes less and less and less and less and converges to negative infinity. In that case, we can say that the problem is unbounded. Think about this. We want to minimize our C transpose X. What is the worst case? Our minimum does not exist. Actually, we can arbitrarily make this objective function value up to minus infinity. In that case, the problem is called unbounded. So this unboundedness is like this. The jth entry is negative and not only the problem is the constraint set is unbounded because of this condition is met, the minimum value is negative infinity. Then the problem is unbounded. Got it? So this is different from this one. Now what if for that yj, rj is positive? What can you say? That's okay. To that unbounded direction, you are not going to move because it increases the objective function value. Got it? Okay, so this is almost the last topic we talk about linear programming. Of course, we are going back to our linear programming problem after we study duality, but not like this intensive study will be done later. Okay. Now we have another review, big picture here. So we really almost are ready to move to the next topic, the last part of our textbook. So I think it's a good time to remind what was the structure of this textbook. First, the first part of the textbook was all about mathematical review of the preliminaries. Two courses were very important. What? Advanced calculus and linear algebra. And we studied many things. And then, what was part two? Part two was entitled as Unconstrained Optimization. However, we studied first order necessary condition, second order necessary condition, and second order sufficient conditions for what? For constraint problems too. And also, in that section, we studied constraint problems, especially one-dimensional line search problems. So we studied what? Golden section, Fibonacci search, something like that. Right? And then we studied something like Newton's method, conjugate direction method, quasi-Newton method, and others. Those algorithms can be used in for the unconstrained optimization problems and also by constrained optimization problems. As you remember, at the last part of the section, part 2, we studied some method to convert constrained problems to unconstrained problems. What were they? For example, you introduce a penalty function so that if your parameter x deviates out of the feasible set, your modified cost objective function increases a lot so that your kind of unconstrained problem tries to push your solution into the original constraint set. And what else? You could also project your solution whenever your next iterate goes out of the constraint set, something like that. But from today, our goal is quite different. So part 4 is titled as Constrained Optimization Problems. And we will study this very intensively, because most of our interesting and important optimization problems not only have some complicated objective functions, but also have some complicated constraints. So let me give you this Venn diagram I've drawn a lot of times already. This is the set of all constrained problems. Among them, there are linear programming problems, as you've seen last a few weeks. Also, there exists some next complicated, little bit more than linear programming problem is so-called quadratic programming problems. You've seen already how to solve a quadratic, unconstrained quadratic programming problem by differentiating and using first-order necessary condition. We may have some constraints. That is called quadratic programming problems. And if you want, you may define your higher order programming problems, but they are in many cases hard to solve. So we devise a new subclass of optimization problems called convex optimization problems. Convex optimization problems have a convex objective function defined on convex sets. So in general, this can be written as minimization of a convex f subject to x in convex omega. Okay. Of course, this is an explicit, so omega that is explicit intersected with implicit is convex, and f is a convex function on this omega. So as you already know, this omega may be any constraint set, but in this case it is convex. Now what does that mean? Our problem is here. F of x may be still convex, but our constraint set may not be a convex set, or f is not a convex set, and omega is f is not a convex function, but omega is convex set, or f is neither f is convex function nor omega is convex set, something like that. Among them, we also consider an interesting subset of constraint optimization problems with inequality and equality, or equality and inequality constraint functions. Consider general constraint set or a feasible set. The question is this constraint set can be written like this? Always? Of course not. Of course not. Okay? Here, this means that you use a finite number of inequality constraint functions and you use a finite number of equality constraint functions. In general, omega cannot be always written in this form. So this set that has, precisely speaking, our explicit constraint set in this form is a subset of the set of all constrained optimization problems. By the way, the lecture note, not by the authors of the textbook, but Stephen Boyd and his co-author, use F vector for the inequality constraint functions and F0 for the objective function. The reason why the Stephen Boyd and the co-author do not use F is that they do not use G is that they use G function for Lagrangian dual function. So anyway, I hope it may not confuse you a lot. But anyway, so this set is related to the constraint set written as the subset defined by inequality constraint functions and equality constraint functions. Then we definitely have this intersected area. The problem is a convex problem, convex optimization problem, and our explicit constraint set is written in this form. The trouble is this: the Stephen Boyd's convex optimization theory is not for this intersected area, but for a smaller area, smaller subset. His convex problem in a narrow sense looks like this. You minimize a convex function subject to our constraint set, explicit constraint set is written little bit have more structure. So we have a convex vector valued function. What does this mean? Each component function is convex. And if you look at the, not this provided lecture note, but some other pages of the original Boyd's lecture note, you will see that this level set is convex set. Anyway, and instead of using general hx equals 0, you have ax equals b. Got it? So Boyd's convex optimization problem considers minimization of a convex function on the intersection of this explicit constraint set and the domain of F0 and F. So where F is convex on omega E intersected domain of F and domain of F vector. Got it? So this is what? This is a convex optimization problem, but have a more structure. Not only general equality, but this linear equality constraint. So please remember this. This is very confusing when you especially self-study Stephen Boyd's optimization theory lecture. Got it? So in general, convex optimization problem has convex objective function on a convex constraint set. But here we have more structure. Convex objective function on convex explicit set with Ax equals b for the equality constraint, and domain of f and domain of f underscore intersected. Now, given that, of course, our linear programming problem is here. So we've studied a very small subset, but interesting one. By the way, in your 645 course that will be offered next semester, the statistical signal processing, many detectors, when you derive many detectors, not many, some detectors, you will see linear programming problems. You need to solve linear programming problems. Got it? So anyway, it's important. So from today, we study this subset. So be careful. We do not study all this set of all constraint optimization problems. We study smaller set. Got it? So sometimes our constraint set may not be written in this form. Sometimes. But many problems that apparently does not have this form of explicit constraint set can be written in this form. So this set is, I believe, big enough for our practical everyday use. It may not be the entire set, but it's big enough. Now, okay, what's wrong? If you take a look at the lecture note I uploaded, we have several topics to cover. First, it talks about Lagrangian dual problem. And next one is called weak and strong duality. And third one is geometric interpretation of actually this weak and strong duality. And next one is optimality conditions. That is actually so-called KKT conditions. And next one is perturbation and sensitivity analysis. And some examples and generalized inequalities. So this is the original items to be covered in the chapter 5 of the boys textbook. And as you have already found that I have removed some of them. So this is gone. But will appear here when you study multi-objective optimization. So anyway, later. Okay. And this part is gone, removed. I think it's too much. But anyway, you need to study when you study convex optimization theory. So these are topics, and you will see, as you will see, first the two topics are related to duality. And what is duality? You've heard this duality, the term duality, and it is sometimes translated as what? How do you translate duality in Korean? It's translated as 상대성. It's not 상대성. Okay? 상대성 is relativity. pair and something like that, right? It is paired. So dual problem is kind of paired with the original problem. What problem? Optimization problem. So this term dual problem has antonym. Original problem, but we usually say primal problem. So suppose we are given an optimization problem, especially a constrained optimization problem, then we somehow find so-called a dual problem. And interestingly, this dual problem is also an optimization problem, has what? Has some property like this. When primal problem is a minimization problem, dual problem is a maximization problem. And second is that this optimal solution, if it exists, has some objective function value, this one, then dual problem's optimum objective function value is what? Less than or equal to this one. So if I somewhat visualize, you have objective function of the primal problem, and you have objective function of the dual problem. So this value is always greater than or equal to this value. Got it? But sometimes, very interestingly, they are the same. So it's like this function and this function touches here. It's kind of oversimplification, but you will see today. So this weak and strong duality means this. Weak duality means we kind of formulate a dual problems in such a way that the maximized objective function value of dual problem is always less than or equal to the minimum value of the primal problem. That is weak duality. Sometimes you formulate a problem so that they are the same. In that case, we say we have strong duality. Got it? So anyway, the first two topics are related to duality. And this KKT condition is also related to this dual problem. So it seems that everything is related to the dual problem. And moreover, this perturbation and sensitivity analysis is related to the dual problem formulation. So it's like this. For example, you had original explicit constraint looked like this. For general, explicit constraint for unconstrained problem. Now, perturbation means that you change this zero vector to some non-zero vector. Say u. Okay? So and h for v. Okay? Here u and v are not zero vectors. And their magnitudes are very small. So little bit change. Then what will happen? Your perturbed problems, we keep our objective function. Sometimes you can little bit modify your objective function, but we don't handle that. We don't think about that kind of perturbation. We perturb constraint set in this lecture note. Okay? Anyway, so what will happen? This set is the intersection of the subset defined by this inequality and subset defined by this equality. Now you little bit change this part by sometimes relaxing, loosening, or kind of tightening your subset. By little bit modifying this one, your subset, your constraint set will change, right? Little bit, if f is especially differentiable or continuous. And if you change this 0 to some v, there will also some change. And this type of perturbation may happen a lot in engineering problems because in engineering there is no zero, right? There is no zero. Under our precision, we may say that is zero, but usually that is not zero, right? So perturbation analysis may be important. And also, this sensitivity is related to this. Suppose you little bit change this one, but suddenly your objective function value changes too much. What does that mean? To have your optimal performance of your, for example, system, you need to be very, very careful by setting your parameters. Slight offset from the optimal value may result in very bad performance when you minimize some cost function. That kind of analysis is, at this point, we have no idea how to perform that. And interestingly, it is not the only way, but interestingly, this dual problem and duality provides us some way, okay? Not the only way, some way to do this perturbation and sensitivity analysis. So this dual problem we haven't yet seen is very, very interesting one. So that's what we are going to study. When I first studied this duality, it was quite confusing. As you've seen from our textbook, the last chapter of the linear programming is about the dual problems for linear programming problems. And the textbook does not carefully describe why this is called dual. Just our textbook say that, okay, here is our grocery stores something, or nutritionist problem. And then think about some related problem for drugstore owner's problem. And then the authors formulate another linear programming problem and say that they are dual. And when I first saw that, why? Right? Actually, general theory, I believe, must be taught first. And you can easily see that that dual linear programming problem, is really an example. Nothing but an example. That's why I little bit changed the order. See that? We studied part 3, linear programming, but moved this part after we study these topics today. Okay? So we just handle duality and linear programming problem as a special case. Got it? Otherwise, it's too confusing. Anyway, so that is the first reason I changed the order. Second one is that, unfortunately, our textbook does not provide a big picture of the entire dual problem or related topics like KKT conditions and those stuff. So if you just study our textbook, you will still be much confused, especially for this constrained optimization problems part with equality and inequality constraints. So that's why I took some parts of the boys' lecture note and teach you today. Okay. So here goes the idea. So first we start from our constraint optimization problem. First we formulate Lagrangian function. Or sometimes it is written as this. As you know, Lagrange is astronomer, and in today's terms, he is a mathematician or physicist. But anyway, this is related to Lagrange's invention. So we call the function we are going to show as a Lagrangian function. The idea is this. Given a constrained optimization problem with inequality and equality functions such that omega explicit is this one. Okay. So given that with objective function f0 of x and equality and inequality functions like this. Okay, I'm not talking about complex function. Okay, I'm just talking about a constrained optimization problem with equality and inequality constraint functions. Got it? That set I've shown you. This set, got it? With inequality and equality functions. So original problem looks like this. We want to minimize f0 subject to x is in the explicit constraint set. By the way, precisely speaking, our constraint set is not this one, but omega sub e intersected with the domain of f0, because otherwise f of f0 of x cannot be evaluated, and domain of f underscore f function and domain of h. Got it? So given that, this is so-called the primal problem. Lagrangian function, Lagrangian, okay, you need to be careful, just a second, Lagrangian, okay, yeah, I'd better say this is just Lagrangian, okay, because there is the function called Lagrangian dual function. Okay, well, I just say Lagrangian function, but many people just say Lagrangian, because sometimes if I say Lagrangian function, many people misunderstands it as Lagrangian dual function. Anyway, Lagrangian is this one. Let's use capital L to denote this Lagrangian function. And its argument is interesting. Of course, you have your original parameter x. Now, this x omega looks like this. And here, first we introduce a vector lambda. And length of this lambda is same as length of f function. So if you have p inequality functions, then your lambda is p by 1. Got it? And also you have another parameter nu that has length same as h. By the way, this is v, this is nu. Okay? Be careful. This is v and this is nu in my handwriting. And this Lagrangian is defined interestingly like this. Original objective function plus lambda transpose f plus nu transpose h. This is the Lagrangian. This is the Lagrangian corresponding to this primal constrained optimization problem with inequality and equality constraint functions. Now, you may be confused. What is this? Okay. So let's see one by one. First, this function includes what? Objective function and inequality constraint functions and equality constraint functions. So our functions in the constraint set is now somehow moved to this function. By the way, we are going to formulate our dual problem with Lagrangian dual function as our new objective function from this one. Not this one, from this one, from this Lagrangian. Got it? So somehow we move our constraint functions to objective functions. Not yet, but you'd better understand that way. Another one, this function has dimension n, right? As you remember. So this is n parameter function. Now what about this function? This is a high function defined in higher dimension. So it's something like this. Probably when you studied your probability course, you've seen so-called Q function defined as the tail probability of this standard normal. So you have some standard normal distribution and define the probability of event this happens as Q function. And also you've seen this Q function cannot be written in a closed function, but has some upper bound, if I remember correctly, something like this. I may be right, okay, when x is positive. Am I right? Let me see. Squared, I believe. Is it squared? What was that? Jung-won, do you remember? I remember it's squared. Yeah. Maybe right. Okay. Something like this. How did you derive? Is it x or x squared? Yeah, I remember it was x squared. Anyway, when you derive this one, the trick is this. This is definitely a one-dimensional integration, but we think in two dimensions. So we consider something like this, x1 and x2, and you have two-dimensional zero mean Gaussian random vector. And you find that this Q function is about, you have x1, x2 lies here with some x here. So you want to integrate two-dimensional Gaussian density here and get Q of x. So the trick is that you transform one-dimensional integration to two-dimensional integration. And then you apply a trick like this. You draw a line, a circle, if I remember correctly, and extend your integration area to this one. So what happens? If you integrate over this area, your probability little bit increases, right? So you have this form. This is easy to, this probability of event that you have some x1, x2 lies here is much easier to compute the probability event that your x1, x2 lies on here. Got it? So this is kind of an analogy. By moving to a lower dimension to a higher dimension, you can now see a wood, not individual tree. So in our Eastern Asia proverb, we now see 숲을 보게 되는 거죠. Not just 나무. Got it? So this is kind of that idea. Okay? We move to a higher dimensional kind of space by formulating the Lagrangian of our primal constrained optimization problem. But what is our objective? In this case, what we wanted to do was to find an upper bound, a larger value of what we want to compute. Now, what do we do? The trick is that since we have a minimization problem, what we want to do is that we want this function provides a lower bound on our optimization problem. What does that mean? Suppose you have an optimization problem like this. And somehow you find that this minimum is greater than or equal to a constant C. Got it? Suppose you can show, given this minimization problem, you have found or you have proved that this minimum value must be greater than or equal to C, some finite value. Then what happens? Actually, depending on how tight, loose, you need to keep these two terminologies in your mind, but depending on how tight this lower bound may be very, very useful or sometimes totally useless. For example, if we do not put any constraint on C, you can always say that, okay, given a minimization problem, trivial lower bound is minus infinity. But that is always meaningless, right? So usually we want some finite lower bound. We love. Now, what would be the best case? The best case is like this. You find some x0 that is feasible. Okay? You find x0 that is feasible and find that when you evaluate at this x0, the objective function value is C. What does that mean? Suppose you have proven this, given the problem. Now somehow you also find x0 that happens to have the objective function value equals C. What can you say? So, story is this. Given the problem, we show this. Now we have x0 like this. Then what? This x0 is a global minimizer. So means an optimal solution, right? Because we achieved a lower bound. Of course, sometimes, be careful, sometimes we find an optimal value and we evaluate our objective function. But it may be greater than our lower bound. In that case, that lower bound is loose. But what does this mean? This means that the lower bound C is, we say, tight. Okay? So as far as we can show that C is a tight lower bound, it's extremely good. Got it? By the way, even if the a lower bound is loose, still it may good. For example, suppose you are given an optimization problem. You don't know how to find analytical optimal solution. So you just use a solver, which means that it numerically searches a local optimal solution. And it says that after many iterations, says that, okay, here is my answer. But definitely, with parentheses, I do not guarantee this is global minimizer. This is a local minimizer. Now, you evaluate your objective function value. And you find that that is very close to your lower bound, somehow differently found. And you know that that gap is small enough. Usually, in mathematical world, any small number is large enough compared to a smaller number. But in engineering problem, we know the gap is very small in many cases. For example, in communications, you know that from history of some theory, many people develop some new decoding scheme that just reduces 0.5 dB, 0.5 and something. Now, nobody knows what is the minimum performance bound, but the current one was here. Now, you derive a lower bound, and your new solution is very close to it, between 0.01 dB. Then, you haven't yet proved it's tight, but you may claim what? I've found near-optimal solution. Got it? So, even a loose lower bound is worth to find. Got it? So, my message is that given a minimization problem, finding a lower bound means a lot in many cases. Got it? Means a lot in many cases. So, let's find a lower bound. But not using an arbitrary way, but some systematic way that is related to this Lagrangian. That is related to formulating this new problem, a new function called Lagrangian. So, as you see here, I exactly followed this page 5-2, but I've used a different notation. I've just written this part as f underscore of x underscore is less than or equal to 0 underscore. I can just use that notation. And h underscore of x underscore equals 0 underscore. And Lagrangian is what? Objective function plus I also used what? This is a summation of product. Whenever you see this summation of products, transform it to what? Inner product. Because that provides you much more information. So I transformed this to lambda underscore transpose f underscore. And this one as what? Nu underscore transpose h underscore. Got it? So as this Buehler says, this is what? Weighted sum of objective, weight is 1, and inequality constraint functions and equality constraint functions. Very interesting. Now, our textbook has a little bit different notation. Instead of using lambda and nu, our textbook uses nu and mu. It's confusing, but it's okay. Okay. But for temporarily, I will follow this lambda nu notation, not nu mu notation. And now, given that, I emphasize that we want to find a lower bound. We want to find a lower bound. Now, suppose here we constrain x to our constraint set. I said constraint set. What does that mean? This x, some x, what? Makes this h equals all 0. Right? So if we constrain our x to our constraint set, this is 0 just. Why do we add, you may say. Got it? This is 0. What about this part? If x is in the constraint set, individual fi of x is what? Less than or equal to 0. Got it? So this is less than or equal to 0. Now we want to have a lower bound. Then what do we want for lambda? Greater than or equal to 0. In that case, what happens? Lambda I greater than or equal to 0, fi less than or equal to 0, multiply, then this product is less than or equal to 0. Now you add up those less than or equal to 0 values, then what happens? This value, when x is in the constraint set, will be what? Will be always less than our objective function value. So it seems that this simple weighted sum of the objective function and inequality constraint functions and equality constraint functions may provide us a lower bound. But here, lower bound for what? For entire objective function in the constraint set. If we restrict x to the constraint set, this is a lower bound. Given of course, given lambda greater than or equal to 0 and nu arbitrary. Got it? So let me summarize. So here, note that if x is in the constraint set, not explicit, just constraint set, okay? So that every f and f underscore h can be evaluated, then f of x greater than or equal to Lx lambda nu for every nu greater than or equal to 0. Okay? F lambda. Got it? Got it? This holds. So, okay. I will write differently. Got it? So Lagrangian has interesting property. If x is feasible and lambda is greater than or equal to 0 vector, then it's as a function of x, it is a kind of smaller function than f of x at any x in omega. Got it? Nu can be arbitrary. This part is very important. Why? Because x is not feasible, what may happen given lambda greater than or equal to 0? Some fi of x may be positive. In that case, this inequality may not hold, right? So this is very important. Lagrangian is a lower bound if x is feasible and lambda is greater than or equal to 0. Now, next page is very confusing. Okay. Now, we have Lagrangian function. Based on that, we define Lagrangian dual function. Or based on Lagrangian function, we derive the Lagrangian dual function. And the dual function is called G. That's why I said we no longer call inequality functions as G, but F. And objective function as F0. you infimize, you just say that this is minimization, but precisely speaking, it's infimization. Infimize Lagrangian function or Lagrangian. But be careful, this is very important. This X is no longer restricted to our feasible set, but domain of objective function and inequality constraint functions and equality constraint functions. Now, let me ask you a question. Omega is a subset of D, or D is a subset of omega, or omega equals D. Which one? In general, omega is a smaller set, is a subset of D. Got it? Why? But what is D, by the way? So D is defined as domain of objective function intersected with domain of inequality constraint functions and domain of equality constraint functions. Now, what is omega? Omega is omega explicit intersected omega implicit. By the way, what is omega implicit? D, right? So, omega is a subset of D. So this is D, and this is omega. Got it? And now some of you remember why I put one problem in the exam 2, where I asked you this one. And omega 1 is a subset of omega 2. What happens? What happens? Here, our constraint set is implicit intersected omega 1, and our constraint set is, which one is bigger? This one is bigger, right? Definitely. What does that mean? So you search for the optimal solution with a bigger space, then you have possibility to achieve lower minimum value. So if you minimize, you have this. Got it? Right? If you minimize the same function, but now your constraint set is smaller, then you perform worse, right? Got it? Proof is not that difficult. You can use direct proof, or you can use proof by contradiction. Suppose this is greater than does not make sense. You have a nonsense, something like that. So keep this in mind. Okay? What? Keep this in mind. Okay? D is bigger. D is bigger than omega. Now let's go back to our lecture note. What if you infimize over X given lambda and nu? Of course, we want to restrict our nu to non-negative, greater than or equal to 0 vector. Lambda is greater than or equal to 0 vector, and nu arbitrary. Of course, it does not say that for lambda greater than or equal to 0, but it's implicit. It's kind of implied, because we want to find a lower bound. So lambda, that Lagrange multiplier, we call Lagrange multiplier lambda must be greater than or equal to 0. Otherwise, it's useless in our search for a lower bound. But anyway, if X is restricted to omega, what will happen? As I told you, this function minimized over X is what? Is a lower bound to our optimal value, right? Now you increase the search space. What will happen? You increase the search space. What will happen? What will happen? So this line is just rewriting of L function here. You define the new function. Now it's parameterized by Lagrange multipliers lambda and nu, because x is gone. X is gone by this infimization. So this value is what? Is it always smaller than our optimal function value? When lambda is greater than or equal to 0? Are you sure? So let's write some lines, because it's real confusing. Okay. You've seen already that L is a lower bound of our objective function value when x is in omega. Am I right? And lambda nu. And now let me write it this way. Am I right? See that? Given this inequality, that holds for this one. I may be placed with this infimize with minimize, but anyway, the same. Infimize, left side and right side, inside this constraint set. Then this inequality holds. Am I right? This is definitely true, because this is true. So no problem. Now, so it's obvious from this line. Now, let's try to lower bound this one. Let's try to lower bound this one. Given lambda, that is non-negative, and arbitrary nu. How can you find the lower bound? If you little bit make the constraint set bigger, then your infimization, minimization may have lower function value, right? So what you have is that some omega prime Am I right? See that? From here to here is obvious. X is still in the constraint set. Now you just focus on this right hand side. Still you keep lambda is greater than or equal to 0. But now you increase the search space like this. Then your minimized, infimized function value given the same lambda nu must be greater than or equal to the previous one. Am I right? So we have what? We have this one. That is what? That is called P star here. The reason why we call this as P star is because this is the function value of the primal problem. So P star is greater than or equal to this one. Now what is this one, by the way? This objective function of this infimization is a function of x lambda nu. But now you infimized over x. So this function becomes a function of lambda and nu. Let's call this function as g. the Lagrangian dual function. So we have what? We have P star greater than or equal to G of lambda nu when lambda is greater than or equal to 0. Got it? This is very interesting, as I told you. We have just found a lower bound to our minimum value. We assume temporarily this is finite. Okay? Got it? So now, this inequality holds for all lambda greater than or equal to 0 and nu. Now, what do you want to do further? Because this value for just arbitrarily chosen lambda and nu may be very loose. Now, what can you do? In order to make this is fixed, in order to make this tight, you want to now maximize this g function. So, new problem is this: maximize the Lagrangian dual function. Of course, this maximization is over lambda and nu. Now, subject to what? The constraint is just this one. This is called what? This is the Lagrangian dual problem, or simply dual problem. Got it? So now, given a primal optimization problem, now you have a dual optimization problem. And we call the optimal solution of this one as D star. So what do we have? P star, that is the optimal function value of the primal problem, is greater than or equal to D star, that is the optimal function value of our dual problem. This is called what? This is called the weak duality. So weak duality means that you formulate the dual problem and solve it. Then the optimal function value of your dual problem is less than or equal to the optimal function value of the primal problem. So this is very obvious. Okay, it seems I just covered half of what I originally intended. But anyway, we have Wednesday. Okay, so let me quickly summarize. What is our goal in formulating this dual problem or something? Given our minimization problem, we want to find a lower bound. That's the idea. Okay? This idea is very, very useful, powerful, and will appear again and again and again whenever you solve, almost whenever you solve an engineering problem. Because engineering problem is an optimization problem. And to find the lower bound, Lagrange's proposal, okay, there may be other approaches you will see. Actually, as you've seen in what? As you've seen in phase 1 of the simplex algorithm. We added more variables, right? So we moved to a higher dimension to find what? To find the basic feasible solution. So that we can ignite our engine, so that some motor can move, right? Almost same idea. We move to a higher dimension. And initially, we wanted to find a simple lower bound function to our objective function inside our constraint set. But now, we minimize the objective function value inside this constraint set, and also this lower bound function. And we have our initial inequality. And then we apply this idea. What if we relax our constraint set from the original constraint set omega to a bigger one? By the way, here I have to emphasize this. Any omega prime can be chosen. But what is the simplest one? One simplest one is the domain of functions. That's why this textbook, this lecture, this note by Stephen Boyd, use D, the domain of objective function, equality function, and inequality functions, as what? As omega prime. By the way, you can use some other omega prime, some other superset of omega. It depends on your choice. So actually, dual function, Lagrangian dual function, is not uniquely defined. It depends on your choice of omega prime. Because if you change this, the function changes. Got it? Anyway, whenever you choose omega prime, great, including omega, the original constraint set, you have this relation. And given that this is constant, so you can maximize this right-hand side. That gives you the dual problem. So you have an original problem that is called now primal problem, and now you have a dual problem. If you solve both of them, or if you just assume you solved both of the problem, what happens? The optimal objective function values of the primal and dual has this relation, because we use a lower bound. And this is called weak duality. Under some constraints, unfortunately not necessarily sufficient, usually sufficient conditions. As you've seen in signals and systems, we never talked about necessarily sufficient condition for periodic continuous time signal is exactly as its Fourier series. We just have seen some Dirichlet condition, that is sufficient condition, right? Similarly, under some sufficient condition, but we believe it's close to necessary and sufficient condition, we can show that P star equals D star. In that case, we call strong duality holds between this dual and primal problems. Got it? Anyway, let's continue this this Wednesday.